I want to start today with a question about how you, personally, learn to do anything difficult.
Okay, lay it on me.
So let's say you're learning to play a really complex piece on the piano. Or maybe you're learning a new language.
Right.
Or even something totally physical, like trying to perfect a tennis serve.
I am terrible at tennis, but I get where you're going.
Well, you have two very distinct ways of getting better at those things.
Yeah. Mostly practice and instruction.
Exactly. First, you have the practice, the repetition. You hit the tennis ball 1,000 times until your arm just sort of, knows the arc.
Right, right.
You play that piano scale over and over until your fingers find the keys without your brain even having to engage.
That's muscle memory. Or, in cognitive terms, implicit knowledge.
Right. Implicit knowledge.
You don't have to consciously think about it anymore. It just happens automatically.
Exactly. But then, on the flip side, there's the other part learning. The coach standing right next to you on the court saying, hey, toss the ball higher.
Or curve your fingers more on the keys.
Yes, or don't rush the tempo. That's the manual. That is the explicit instruction.
Right. The declarative knowledge, basically the rules of the road that guide your muscle memory.
And in the world of artificial intelligence, specifically large language models, we have historically treated these two things, the practice and the instruction, as totally separate universes.
We really have. They're entirely different phases of development.
But we have a paper on the desk for today's deep dive that suggests, well, that we've been doing it wrong, or at least that we've been missing this huge opportunity to combine them.
It is a fascinating paper. It came out in February 2026, and it's titled Evolutionary System Prompt Learning for Reinforcement Learning in LLMs.
Which is a bit of a mouthful.
It really is. So, for the sake of sanity, let's stick to the acronym the researchers use, which is ESPL.
ESPL. Got it. And the core promise here, the mission statement of this paper, is just wild to me.
It's definitely a paradigm shift.
It's essentially asking, what if the AI could rewrite its own teacher's manual while it was practicing the piano?
Yes. What if it could evolve its own instructions to get better, faster?
Exactly. So, for everyone listening, we are going to explore how breeding better prompts while training the digital brain creates this incredible feedback loop.
A loop that drastically improves both reasoning and generalization.
So, let's set the scene for the listeners. How do we typically train an AI model today?
Standard operating procedure.
Right. Like, if I want to make a model better at math, what do I usually do? Because I've always just assumed it's, showing it a ton of math problems.
Well, usually you have two main levers you can pull, and they are pulled by completely different teams of people at different times.
Okay, lever number one.
Lever number one is training the weights.
The weights?
Yeah, you take the neural network, the actual digital brain with all its parameters,
Yeah.
and you run it through millions of examples.
That's a heavy lifting.
Right. You use reinforcement learning, or RL. If the model gets the math problem right, the specific digital neurons and connections that led to that correct answer get strengthened.
And that's the muscle memory part we were talking about.
Precisely. That's the procedural knowledge. But it's slow. It's incredibly computationally expensive, and honestly, it's very hard to tweak once it's done.
So what's the second lever?
Lever number two is prompt engineering. This is where you don't touch the digital brain at all.
You leave the weights alone.
Exactly. You just change the text instructions you feed into the context window.
Manual.
Right. You type in something like, "You are a world-class mathematician. Please solve this and show your work step by step."
And usually these are two totally different jobs.
Completely different. You have these heavy-duty researchers training the weights in massive server farms for months.
Right, spending millions of dollars on compute.
Yeah. And then, much later, you have prompt engineers tweaking text files to try and coax the absolute best performance out of whatever brain the first team built.
They rarely talk to each other during the actual process.
Almost never. And the breakthrough in this ESPL paper is the realization that these two levers just shouldn't be pulled separately.
They need to be pulled simultaneously.
Exactly. Because if you think about it, a better manual makes the practice more efficient.
And better practice reveals exactly what needs to go into the manual. Okay, so explain the mechanism here. How does ESPL actually work under the hood?
It's a really elegant setup.
Because my mental image right now is just an AI sitting at a desk with a red pen, grading its own papers while simultaneously doing push-ups.
That's actually not too far off the mark. But instead of just one AI trying to do everything, I want you to imagine a whole population of instructions.
A population, like
Yeah.
a bunch of them.
Yes. The ESPL system doesn't just start with one fixed system prompt like "you are a helpful assistant."
Right.
It generates a whole pool of different prompts, different variations of instructions, different logical strategies, even different tones of voice.
Okay, so we have prompt A, prompt B, prompt C, all the way down the line, and they're all slightly different.
Exactly. Now, the model tries to solve a batch of problems.
What kind of prompts?
In this specific paper, they focused heavily on complex math and agentic search tasks.
Got it.
So it tries to solve these using those different prompts from the pool. It goes through the standard reinforcement learning process to update its weights based on whether it got the final answer right or wrong.
Which is the muscle memory building up. That's standard RL stuff so far.
But here is the major twist. The system treats every single training step like a tournament.
A tournament.
Yeah. It tracks which specific prompt led to the correct answer for the model.
Oh, I see. So if prompt A told the model to, say, double check your math at the end, and that led to a win,
Right.
but prompt B told it to guess as quickly as possible, and that completely failed.
Then prompt A wins that round. The system actually uses a Bayesian rating system called True Skill.
Wait, true skill?
Yeah. It's the exact same ranking system used in online video games to match players.
Like in Halo or Call of Duty?
The very same. They use it to rank the prompts based on their relative performance against each other.
I love that. So the prompts are literally climbing a competitive leaderboard based on how genuinely helpful they are to the model's brain.
Exactly. The prompts that lead to success get a high rating and they survive. The bad prompts that confuse the model or cause hallucinations, they get dropped.
It really is survival of the fittest, but applied to text instructions.
Pure evolution. And
Okay.
you can actually visualize it as this massive evolutionary tree where prompts are branching off and competing over time.
But hold on, if we just pick the winners from that initial batch, we're going to plateau eventually, right?
How do you mean?
Well, evolution requires change. It requires new genetic material. If we just keep selecting the best of the starting group, we aren't creating anything novel.
Yeah, you're exactly right. And that brings us to the genetic operators in ESPL.
The mutation and crossover stuff.
Correct. The winning prompts on that leaderboard don't just sit there. They become parents for the next generation.
Okay, let's dig into the mutation part first, because in real biology, mutation is just random.
Right? Cosmic rays hitting DNA.
Yeah. A ray hits your DNA, and suddenly you have a slightly different protein. Is the AI literally just randomly deleting words from the prompt and crossing its fingers?
Because that sounds chaotic.
It sounds like a great way to break a language model.
It is. Random mutation in AI usually is a disaster because human language is so fragile. If you randomly change the word not to now, the whole instruction breaks.
Right.
So ESPL doesn't use random mutation. It uses a process of self-reflection.
Self-reflection. How does a prompt reflect?
It's brilliant. The system takes the best performing prompt from the leaderboard. It looks at the specific training examples where the model still failed despite having a good prompt,
Okay.
and it performs a postmortem. It essentially asks a reference language model, hey, we used this top-tier prompt, but we still got this specific math problem wrong. Why did we fail?
It analyzes its own failure trajectory.
Exactly. It looks at the step-by-step attempt and finds the bottleneck.
Like maybe the model rushed the division step or it hallucinated formula entirely.
Right. And then, based on that exact failure, the model proposes a highly specific edit to the system prompt to fix that weakness.
So it's not random at all. It's a targeted surgical fix.
The researchers actually describe it in the paper as being like a git diff.
Like a programmer submitting a patch to a code base.
Yes. It's debugging its own operating instructions.
It says, I keep messing up geometry proofs, so I am going to write a new permanent rule in my manual. Always draw the diagram first.
That's exactly how it works.
That is incredibly powerful because it's completely reactive. It's learning directly from its own specific failures rather than just guessing what might sound good.
Right. It's a closed iterative loop of self-improvement, but happening entirely on the declarative instructional level.
But that's just the mutation side of things. There's also crossover,
Yeah.
which in biology is mixing the DNA from two parents. How do you mix two text prompts together without making a mess?
Well, here it's all about combining proven strength. The system maintains what they call a score matrix.
Okay, a score matrix.
It notices, for example, that prompt A is absolutely crushing it on all the algebra problems in the batch.
Right.
But prompt B is significantly better at handling the geometry questions.
And in a normal, traditional training run, you'd basically have to just pick one and lose the benefits of the other.
Exactly. You'd say, well, algebra is more prevalent in this data set, so let's stick with prompt A.
But the crossover operator says, why choose?
Right. It takes the algebra instructions from prompt A and the geometry instructions from prompt B and literally welds them together.
Creating a child prompt, a super prompt.
Hopefully, yes.
Hmm.
A prompt that is good at both. And this addresses a massive known problem in AI training called catastrophic forgetting.
Oh, where it learns a new skill but entirely overwrites the old one.
Yes, it learns how to do geometry, but suddenly forgets how to solve for x.
Right.
By keeping the successful instructions from different lineages and systematically combining them, ESPL prevents the model from forgetting good strategies while it learns new ones.
So what we have here is a model that is building its muscle memory, the weights, while simultaneously writing a better and better textbook, the prompts for itself to follow.
And this synergy, this distinction between the weights and the prompts, is really the philosophical core of the whole paper.
The procedural versus declarative knowledge thing.
Yes.
Explain that distinction a bit more for the listeners, because I really think that is the key to understanding why doing both at once works so much better than just throwing more computing power at the weights alone.
Sure. Think about the classic rule, don't touch a hot stove.
Okay.
Procedural knowledge, which maps to the AI's weights, is learning that rule by actually touching the stove 50 times and getting burned.
Ouch.
Right. It's slow, it's painful, and it takes a lot of trial and error to encode that intuition.
My hand hurts just thinking about it.
Exactly. Declarative knowledge, which maps to the prompt, is your mom just verbally telling you don't touch the stove, it's hot.
You learn it instantly.
Yes. It costs almost nothing to learn, and you can articulate it.
So ESPL is basically moving the high-level rules out of the expensive, slow-to-train neural network and moving them into the cheap, instantly adaptable text prompt.
Spot on. By offloading the logic, the specific workflows, and the strategies to the prompt, the weights don't have to essentially memorize everything.
They can just focus on execution.
Exactly. The weights handle the raw mechanics, the intuition, the know-how, while the prompt handles the strategy.
I like to think of it like a chef in a restaurant.
Oh, that's a good analogy.
The chef really needs excellent knife skills and an intuitive sense of timing. That's the weights, that's the muscle memory.
Right.
But if they have a perfectly written recipe card taped to the wall, the prompt, they don't need to waste brain space memorizing the exact ratio of flour to sugar for every single dish.
That is the perfect analogy. The chef improves their technique every day, and the recipe gets refined every day.
And the data totally bears this out.
Yeah.
But honestly, the most fun part of this paper for me was actually reading the text of the prompts the AI wrote for itself.
Oh, they are fascinating.
Because remember, you listening to this, no human wrote these instructions. The AI evolved them.
Let's talk about the agentic search example first.
Yes. This was where the AI had to act like a research assistant, right? Using a search engine like Google or Wikipedia to actively go out and answer complex questions.
Correct. Now, the baseline prompt, the one the human engineers started the system with, was very generic.
It was probably something like, you are a helpful assistant, search the web for the answer.
Standard stuff. Just basic declarative knowledge.
But after going through the ESPL evolutionary process, the prompt got very opinionated.
It really did. The system invented this rigorous workflow it called a verification block.
A verification block.
It started demanding that the model explicitly output a status of either verified or not verified for every single search result it pulled up.
But it wasn't just slapping a label on things. It actually defined what verified meant in the prompt. This is the part that got me.
Yeah, it explicitly learned and then wrote down the rule that a result is only verified if the web domain ends in .org, .edu, or .gov.
Or if it's a major legacy news outlet like Reuters or the New York Times.
Exactly.
That blew my mind when I read it. The AI essentially invented standard journalistic fact-checking on its own.
It did. No human engineer went in and told it, hey, don't trust random blogs or social media.
It just naturally learned through reinforcement that when it relied on .edu sites, it got the right answer more often and won the tournament. So it codified that into a hard rule.
And it created an operational loop. It wrote a secondary rule in the prompt that said, if all results are not verified, modify the search query and repeat the search.
It's almost like it developed a conscience or, a very strict human editor looking over its shoulder.
A digital conscience is a great way to put it. It's a self-imposed constraint to ensure quality. It found a negative pattern, bad sources equal bad answers, and it wrote a literal law into its own manual to prevent that pattern.
There was another example in the paper in the math section using the DeepSeek v3.1 model. I thought this one was even more telling.
Oh, the sanity check example.
Yes.
This is a classic example of emergent behavior. So the model is trying to solve a really complex competition math problem from the ARM dataset.
Really hard high school math.
Right. Number theory. So it does the derivation, it uses the formulas, it grinds through the logic, and it arrives at a final solution.
And normally, a standard model would just output that answer and proudly move on.
And it would often be confidently wrong.
Right.
But here, the evolved prompt stepped in. The prompt had naturally evolved a specific heuristic over time.
An instruction that said something like, test small instances to verify consistency.
Yes. So the manual basically forced the model to pause before answering. The model went back and tried plugging in n equals 2 and n equals 3 into its own formula.
Sanity check.
And it realized, wait a minute, this physical plausibility check doesn't match my derived answer.
It caught its own mathematical error.
It caught the error, backtracked,
Yeah.
found this mistake it made earlier in the derivation, fixed it, and then output the correct solution.
I mean, that is the holy grail of AI reasoning right there. We talk so much in this industry about chain of thought, but this is an actual chain of verification.
And again, it wasn't hard-coded by a human engineer sitting in a cubicle. The AI learned through evolution that checking your work is a winning survival strategy.
It's the difference between a student who just wants to finish the test as fast as possible so they can go to recess and a student who genuinely wants to get an A.
That's a great way to look at it. The ESPL process effectively evolved the persona of a straight A student.
Now, I do have to play devil's advocate here for a minute,
Please do.
because evolution is messy, it's blind. And sometimes in biology, you evolve a trait that looks really good in the short term, but is actually just a weird shortcut.
Right.
Did the researchers find any weird evolutionary quirks in the prompts? Because usually these RL systems are famous for finding loopholes.
They definitely did find some quirks. They call it the overgeneralization risk in the paper.
Right, the graph theory mistake.
Yeah, that's the one. So the system was trying to solve a batch of problems involving minimum T-joins in graphs.
Which is a very specific, fairly dense mathematical concept.
Very dense. And the prompt evolved a rule to help the model solve it. The rule said, pair vertices along efficient paths.
Which, to a layperson like me, sounds completely reasonable.
It sounds very intuitive. And the thing is, for the specific training data it had seen, that heuristic worked almost every single time.
But mathematically speaking.
Mathematically speaking, it is not rigorous. There are specific edge cases where that heuristic completely fails to find the true minimum T-join.
So it learned a rule of thumb, not an actual law of mathematics.
Exactly. It sacrificed absolute perfection for a handy shortcut. It behaved exactly like a student cramming for an exam who memorizes a neat trick rather than actually understanding the underlying theory.
But, and I think this is a huge but, this failure mode actually highlights one of the biggest benefits of the entire ESPL framework.
The transparency aspect. The glass box.
Yes. Explain that idea for the listener.
Well, think about a standard AI model. If a black box AI learns a bias or a bad mathematical shortcut entirely inside its neural weights, we cannot see it.
It's completely invisible to us.
Right. It's just a floating point number buried in a matrix of billions of parameters. We have absolutely no idea why it's getting the edge cases wrong. We just see the wrong answer.
We just shrug our shoulders and hope more data fixes it.
But here, with ESPL, the bias or the shortcut was written out in plain English inside the system prompt.
The researchers could literally just read the prompt, see the line that says pair vertices along efficient paths, and go, aha, that's the error right there.
Precisely. It turns the traditional black box into a glass box, at least for the high-level reasoning and strategy.
That is a massive safety and alignment feature. If the AI is writing its own logic out in text, we can audit the logic. We can step in and correct the manual.
You can actually debug the AI's thought process because the AI kindly wrote its thought process down for you.
Okay, let's talk about the bottom line results here. Because concepts are fun, but does this method actually produce smarter models?
Or is it just a cool science experiment?
Right. Are the numbers there?
The numbers are definitely there, and they're significant. Let's look at the AAE 2025 math competition test.
These are the hard high school math problems that filter kids for the Math Olympiad.
Right, exactly. Very tough benchmarks. Doing just standard reinforcement learning training on the weights got a success rate of about 56.3%.
Okay, 56.3.
Adding ESPLSO, breeding the prompts alongside training the weights, bumped that success rate up to over 60.6%.
Wow.
In the world of competitive math AI, where researchers fight tooth and nail for gains measured in fractions of a percent, a 4% jump is huge.
But the real story in the paper isn't just the raw score, is it?
No, the most impressive finding is the generalization.
The easy to hard test.
Right. This is kind of the ultimate test of true intelligence.
Mm.
Can you learn a concept on relatively easy problems and then successfully apply that knowledge to a completely different, much harder problem that you have never seen before?
So they trained the system on the standard Amy dataset and then tested it on.
A dataset called Beyond AIM, which, as the name implies, are significantly harder problems.
Okay.
Standard RL alone really struggled here. It improved a little bit, hitting about a 38.8% success rate.
38.8.
But the ESPL-trained model jumped to 45.1%.
That is a massive gap in generalization.
Tells us something fundamental about learning. Good instructions, having a good manual, helps you survive in unfamiliar environments much better than just relying on muscle memory alone.
Because if you encounter a problem you've literally never seen before, your muscle memory naturally fails. You don't know the song yet.
But a good declarative strategy, things like check your work, verify your sources, try small numbers first to test the logic, those strategies apply everywhere.
Exactly. ESPL is essentially teaching the model how to think about problems, not just what to think about a specific problem.
It provides a cognitive scaffolding that supports the model, even when the environment gets much tougher.
So, zooming out to the big picture here as we wrap up, what does this mean for the future of AI development?
It feels like a turning point, honestly.
It really feels like we are moving away from humans micromanaging these models.
We definitely are. The paper strongly implies that nature, the architecture, and the weights and nurture, the prompts and the context, have to evolve together.
We can't just build a giant brain and hope for the best. We have to let it build its own thought processes.
And right now, the model is just editing its system prompt. It's essentially just rewriting a text file.
But where does this go next?
Well, the authors briefly touch on a concept called self-referential recursive self-improvement.
Which sounds exactly like the old seed AI concept.
It is seed AI. Right now, the AI changes its instructions, but in the near future, maybe the AI edits its own underlying code. Maybe it changes its own training algorithm to be more efficient. If ESPL proves that the model knows how to optimize its own learning process better than human engineers do, why wouldn't it eventually know how to optimize its own architecture better than we do?
We are taking the training wheels off. We used to painstakingly write the prompts. Now we are letting the AI write the prompts. Next step, we let the AI build the AI.
And ESPL is a concrete, working, proven step in that exact direction. It shows that the AI can act as a rational agent that reflects on its own behavior and iterates.
I failed, therefore I will change my internal rules so I don't fail next time.
That is an incredibly powerful loop. It's becoming a reflective practitioner, and it's doing it effectively for free during the normal training process.
You're generating the data anyway. Why not use it to improve the manual?
Exactly.
Well, I want to leave you, the listener, with a final thought about that digital conscience we mentioned earlier.
It's a heavy thought.
Right now, a system prompt is almost always something a human writes. It is us telling the machine, be safe, be unbiased, don't be rude.
It's an external constraint, the laws of robotics, handed down by humans.
But in an ESPL system, the AI takes over the pen. It starts writing its own rules.
Right.
So at what point does the system prompt stop being a user manual that we provide and start becoming the AI's own internal monologue?
That really is the question, isn't it?
If it is constantly telling itself, be honest, check your work, don't trust that sketchy source, is that just a line of code? Or is that the beginning of a personality?
If the AI is independently deciding what its own values and rules are, based purely on what helps it succeed in its environment, that changes the whole game.
It's no longer just following our orders, it's forming its own habits.
Definitely something to mull over.
Something to mull over until next time, indeed. Thanks for joining us on this deep dive.
Yeah.